if you wouldn't mind queuing up the recording. Perfect. So hi, everyone. Good to see you again. Oh, 8, there we go. Okay, so this one's a little bit tricky. So the question is, match the term with the correct definition. So the good news is that it looks like, so the way we read this is each of these answers has a count plot with the number of people who answered each different match. So I know it's a little bit confusing, but I think this is a good reminder. So what is a hidden layer? A single or multiple node that transforms inputs into outputs. Hidden layers, someone said within the node, it transforms the output of the node. So a hidden layer is correct. The majority of people said single or multiple nodes that transform inputs into outputs, right? So it's by definition in the middle. It's hidden because we, as the operator of the neural network, we can control the input and we can tangibly see the outputs. But in the majority of neural networks, it's not really clear what is happening in the hidden layer. Something's being passed in, something's being passed out, and we will just see the input and output. So hidden layer, nice job. An activation function. So the most common answer was within the node transforms the output of the node. So this is correct. So the transformation function, also called a transfer function, and the example we talked about last night was the sigmoid function. We'll use that again tonight, the so-called squishing function. Basically, it acts within the node and it provides, it transforms the output of that node. Okay. Gradient descent. I'm glad everyone got that one right. So it's an optimization algorithm, right? Now that is distinct from backpropagation. So we'll talk about that in a minute, but backpropagation, it calculates the gradient, and gradient descent is actually the algorithm that optimizes or makes adjustments based on that gradient. Okay, so they're actually two different things. An epoch is one iteration in training a neural network. Awesome. I don't know why they don't just call it an iteration. You got to speak the lingo, right? A hyperparameter, a setting that adjusts how an algorithm learns. Very important one, back in unit 2, I think, right? And there's, yep. So good job, the majority got those right. Okay. Oh, I love this, guys. Thank you so much for taking the time to write such thoughtful answers to this question. I mean that sincerely. And if you want to put an emoji after the paragraph, that's okay. Like if you want to be like question mark, but you can't have your whole answer be an emoji or ASCII art. Okay, so let's go ahead and look at a couple of these answers. So this is, I was actually talking with the TLs before class, how the question often arises, how do you choose what model to use? What approach do you want to take, right? And the approach you've been taught to date is to take the, so thank you, Dakota, for contributing that. You start with a dumb model, right? And then you get a baseline, and then you walk up to more complex models. And basically, if you can beat it with a more complex model, you use a more complex model. That's what the Kaggle exercise taught us, right? You know, you just want to optimize for accuracy, and like, he who gets the most accurate model wins. Well, unfortunately, that's not quite how data science works in the real world. And so my goal for this question was to have you think about that decision. And so in my experience and the experience of other data scientists, you often make decisions about what model depending on what the objectives are. And so, for instance, if you're trying to put together a data science product, like you work at a startup and it's selling something like a health score, or in the case of my company, it was, when I worked in biomedicine, it was predicting fertility rate. And accuracy is important, right? You want to optimize for having the highest number of true positives, or just the best estimate of probability. However, we didn't use a neural network for that. We actually used a much dumber model. And the reason is, in part, neural networks didn't outperform the simpler models. And so that meets the criteria we were talking about earlier. However, more importantly, and pertinent to this question, physicians, who were kind of the main customers of our diagnostic tests, so we weren't selling to consumers like 23andMe, it was physicians because it was a medical test. And physicians have to make evidence-based decisions. And because they're very, very skeptical, not all of them, but a lot of them are, and they want to understand how something works. And so part of the decision that impacted our choice of model in that case was, what can we explain, right? And so in this case, the trade-off between interpretability and accuracy is often that those simpler models, and actually there's a, let me find that figure, versus accurate machine. I just paused my sharing, but I want to pull up, I have a favorite figure here, and you guys have probably seen it before. Assuming this is going to load. Anyway, but effectively there's this, okay, so this is what I'm looking for. So there's often this trade-off where you can have something simple, in our case, like a decision tree, not a random forest, but a decision tree in a linear regression model, where you can explain it, right? You can interpret what each split means in a decision tree. You can interpret the coefficients in a linear regression model. Things start getting more opaque and less overtly interpretable as you go down this. However, there's also, as you get to these more complex models, such as neural networks, as we're diving into today, you get this trade-off where they're way more accurate. But as we will see painfully today, as we walk through step by step a multi-layer perceptron, the interpretability you begin to lose that, right? It's going to take me half an hour to walk through one iteration of it, making sure you guys understand backpropagation, gradient descent, and the whole feed forward algorithm step by step. Imagine explaining that to a product manager. It's not going to happen. And so as a data scientist, the point of this question was to highlight the fact that it's not always the most accurate model that wins. It really depends on your stakeholders as well. So, but also, and I would love to, let's also see what you guys contributed. That's my rant. Let's hear what you guys would answer. Accuracy is not worth sacrificing in complicated issues. And actually it's true. It may just be that the problem itself, if you're predicting New York City rental prices, it might pretty easily predict it with a linear model, right? And if it's got a high enough accuracy, great. You don't need, there's like, why, if you've got a decently performing model that's simpler, do that, right? The more accurate we get, the less we're able to interpret our model. If you need accuracy, yep, exactly. You need to be able to explain your results, stick to more traditional, right? A bit of a black box. High accuracy. Ooh, good call out for non-linearly separable classes. And so this is something that we touched on, but didn't actually speak directly to. So the perceptron in particular is good for linearly separable classes. So remember that iris example we had, and we had some stuff down here. A linearly separable class is something where you can just draw a line through it and segregate between the two. So a perceptron, the main criticism of a perceptron as a model when it came out in the 50s was that it isn't linearly separate. You can't, it fails at this task, right? However, as we get multi-layer perceptrons and more sophisticated neural networks, we can actually start attacking these non-linear problems. Okay. Predict, we need, okay, but I love this call out. We need to check the model for implicit bias, actually. So no model is going to be perfect if your data sucks. And so if there's bias in your data set, you're going to have bias in your predictions. And I don't mean the mathematical sense of bias. I mean like selection bias. I mean literally it's going to be a biased result. Classic, help you understand. Neural network, maybe magic. Yep, I think it looks like everyone really has I really appreciate the answers here. These are great. Less parameters, we'll have a larger data set, generalization nonlinear mapping. Oh, this is a good one. Actually what I love about this one, I haven't actually finished reading it yet, but I love that there's an example. I'm not a sports fan, and I'll say that again and again and again. However, an example is a fantastic way to illustrate your point in an interview. I could tell them with 1% accuracy. I could only give them results in Klingon script. That's the trade-off between interpretability and accuracy, right? Okay, I understand what you're saying here. So, okay, awesome. These are great answers, guys. Cool. So before we dive into tonight's seminar, are there any questions or any thoughts that someone might like to add to any of these?
Just one question, just to clear up the one statement about implicit bias. Mm-hmm. Is the classic versus the neural network models do a better job?
Oh no. Garbage in, garbage out is a universal thing. So if you can't compensate for bias in a way, and like one way to think about it is like the classic example is like, let's say we've got again with my beautiful diagrams, let's pretend this is a dartboard, right? And let's say that this is kind of like our true prediction that we're trying to get at, right? If the sample that we're pulling from is only this part of it, right? You can get no more amount of data is going to like move this closer to the center, right? If this is what you're pulling from. If there's some bias that has led your sample to be skewed, to one direction, no better model, what you need to do is you actually need to go back to the, oops, sorry, I resume share. No better model is going to be able to compensate for that. Does that make sense? Yeah, so actually, I really wish they spent more time talking about experimental design. So don't be surprised if you see some quiz questions in there. Again, not to scare you, just to politely remind you about different types of bias and acknowledge that it exists. Self-selection bias, survivorship bias are two big ones, but we have enough to cover, so I'm not going to go down that rabbit hole tonight. But thank you for that question, Martin. Okay, let's go ahead and dive into tonight's notebook. Okay. So tonight, I wanted to spend a couple of minutes revisiting my explanation of how the eye works. And the goal, I think that it was I think I didn't deliver it quite as effectively as I wanted to. And so just to talk about what I intended to convey, let me just very briefly explain the metaphor that I'm going with tonight. And it's a fantastic introduction because what we're talking about tonight, what we did last night, was we talked about effectively a single neuron, right? And how you've got data coming in, right? That data can be added up over time. You've got input coming in. There's a transformation function that happens in the neuron, and then that produces an output, right? And so that's your action potential. Now, in the analogy of a multi-layer perceptron, the eye is a pretty elegant example, actually. And so the way the eye works is that you have these individual neurons. So these are called rods and cones. And so these are the things that detect color, You know, we see 3 different colors, or we have 3 different types of cones because we can see different, and that's how we can see the spectrum as we do. Dogs only have 2 cones, and so they actually see the world as kind of a gradient of greens and grays, and because that's what they're most sensitive to. They have 2 types of cones, we have 3. So we have these rods and cones. These are firing in response to certain colors and certain photons of particular wavelengths hitting them, right? So then what happens is when that fires, you have these other neurons, so you have these neurons sending messages to a different neuron, to a different layer, right? And in this analogy, the input layer would be our rods and our cones. The hidden layer would be these cells in the middle. And bipolar cells are cells that act in response to the cones and the rods. Okay, so they, for instance, they'll help us detect and enhance patterns and contrasts. Okay, and then our output layer would be this, the ganglion cells. And as you can see here, this is literally the axon of the optic nerve. So this actually goes to the brain. And so you have like this really cool little neural network in your eye. You have input coming in, you have a hidden layer, which we can't really detect. What we can see, we know the light that's coming in, we can see the light, right? And then on the other side, we have messages being sent to the brain that we could theoretically measure if we were you know, looking at the neural potential of the change in whatever signal, whatever electrochemical signal is being sent down the optical nerve. Okay, so hopefully this tells the story of a multi-layer biological neural network in a little bit more of an elegant way. And I do not want to get sidetracked into the biology as much as I would love to have that conversation. We'll save that for office hours. Okay, so coming back to the neural network, to the artificial neural network, what did we learn yesterday? Well, we learned that there, oh, did someone speak?
Yeah, can I just ask you to please share the call-up with us? I don't think we have
I'm sorry.
permissions.
I thought I did. I think I might have forgotten to press enter. Oh, you don't have permission. Okay, let me see. Okay, let me see. Edit. Oh, I think I understand. So when I share something, if you're logged into your Lambda account, it will automatically allow you to. Let's see, share, advanced, change. Okay, so now anyone with the link should be able to view it. I'll go ahead and,
Thank you.
Yep, thank you for that call out. Okay, there we go. Okay, so what did we review yet, or what did we learn 2 days ago? Wasn't yesterday. In our last meeting? Well, we have input layers, we have hidden layers, and we have an output layer. And in this case, we have 4 input neurons or nodes. They mean the same thing. And we have one node or one neuron in the output, which means that we have 4 features that are being plugged in, and we have 1 output. Okay. And each neuron has its own activation function, okay? So how do we apply the weighted sum that we discussed yesterday? So remember, we talked about we take the weight of input 1 plus the weight of input 2 plus the weight of input times input 3 plus this bias term. Well, when we start getting into multi-layer perceptrons or multi-layer networks in general, each of these lines represents an input weight combination that we're going to be multiplying together and then adding together. So here we have, so for each neuron, we've got 4 neurons in the input layer. We have 1, 2, 3, which means we're going to have a total of 12 elements when we're putting together our summation function, right? That's important because we're actually going to walk through an example later. So how do we, broadly, how is signal passed through? We take the inputs from the training data, we apply these inputs to the corresponding weight. So in this case, we would have 12 that we apply to. We add bias to the weight. We apply the activation to the whole thing by squishing it, right? And then it gets passed into the next level, right? And so this would basically be one epoch or one iteration of the neural network. So thinking about this in a more formal way, and we'll define some of these terms, but it is important that you are familiar. So in total, this is what we call a feed-forward network. The reason being, information comes from the input and goes to the output. There's no feed. Remember those feedback loops that I was referring to, where they can kind of like, information can come and move backwards in the neural network. We will talk more about those later, but a feed forward basically has arrows just going in one direction, and that is from right to left in this case, or left to right in this case. So formally, how does this work? We have, when we're defining our network architecture, we do this in a couple of different ways. So we have the number of inputs, right? And so that's the number of neurons. So in this case, it would be 4. Number of outputs, or number of classes we're trying to predict. So as an example, if we were to predict in like, we briefly talked about how neural networks can predict multiple outcomes. Well, one that may look like predicting multiple classes. So for instance, it may produce an independent probability of being class 1, 2, or 3, right? So the number of outputs could be equal to the number of classes. And the number of hidden layers, or number of neurons in each hidden layer, is a little bit more abstract. That's a hyperparameter that we will touch on later. But for now, we're going to try to keep it simple, and it's going to be complicated enough without trying to add 16 neurons in our hidden layer. Okay, so we're going to randomly initialize our weights. We did that last night. We're going to implement forward propagation. We're going to define this in a minute. The main thing that I want you to take away from this is that you're going to compute what's called a cost function, okay, J of theta. For any of you guys who have watched Andrew Ng's, I mean, when I say J of theta, I still hear it in Andrew Ng's voice in my head. It's like every other word out of his mouth in his Intro to Artificial Intelligence course, or in his Intro to Machine Learning course, which if you haven't watched it, I highly recommend it. So J of theta. So this is something that we're going to call a cost function. This is related to error. We're going to implement backpropagation to compute partial derivatives. That's way more complicated than it actually is in practice. We're going to use gradient descent to minimize J of theta as a function of our parameter theta. Okay, so this gives you the official notation. If you were to write out a formal proof of how a neural network works, this is what you would use. I'm more concerned about the intuition. Okay, so let's define a couple of these terms. You're going to hear me use the term cost, loss, and error pretty interchangeably. And I know I'm not your only instructor that does that. So go ahead and speak up, unmute yourselves. When you think about error, what comes to mind? What are some error metrics that we've used in the past?
The delta of the theory of measurement.
The delta of the, sorry, what did you say?
I said the delta of the measurement in the model.
So you mean accuracy, like the difference between the true and the...
Yeah.
Yeah, exactly. So accuracy is one. What are some other error metrics we've used? Because I know accuracy isn't the only one you learned.
Mean absolute.
Mean absolute. Error, absolutely.
R-squared.
R square is based upon the... Yes, you can use it to assess the quality of your model. It's not quite error, though. It's a little bit different.
Well, Gwen took mine, so.
What's that?
I said Gwen took mine, so I had to come up with something.
Okay. So I would say the residual sum of squares, which kind of leads into R squared. The root mean squared error. Yep, exactly. So perfect. So you guys are familiar with this. I mean, of course you are. I know you are. I just wanted you to think about it. You know, how would we define error and accuracy before? I see one more person typing. Are there any that we've missed? ROC, AOC. So that is one way to, it's not a traditional error metric, but it's definitely a method to, and it would actually be ROC, AUC, area under the curve for that metric. That's actually my favorite metric. It's not strictly an error calculation because it actually is actually the trade-off between false positives and false negatives. So it actually is a more balanced metric. An F1 score is one that you guys may or may not have heard of. It's actually not, it's rarely used in practice, but it's worth knowing. Okay, awesome. So so what is cost, loss, and error? So an error in this case is going to be, as Martin said at the beginning, for most situations is going to be calculated by taking the difference between the predicted and actual value. But what we're going to do is we're going to take the square of it. And so, again, comments about the overall quality of a network's prediction by looking at the average error across all observations, mean squared error being an example. So how does this relate to what we're going to be talking about tonight? Where's my little diagram? Okay, so I actually wanted to talk about the intuition of gradient descent before we dived into the formal explanation of it. So gradient descent simply means that it takes a gradient. A gradient is the derivative, for those of you guys who haven't forgotten your calculus. In other words, it's the slope of the line, right? And so if we're looking at this, we have the slope of our line here, right? Let's say that this is our optimum value, right? So formally, our cost function is going to be plotted on the y-axis. So this would be j of theta, right? And so theta being whatever parameter we're trying to optimize for. The weight is actually theta, okay? And so what we're going to do is we're basically going to take a step in a given direction, right? And so if we take a step from our randomly initialized weight in this direction, right? If we readjust, we recalculate our weights against the inputs, we can actually see that we're close to what it should be, right? And so, however, if we were to step in this direction, right, this would result in a larger error. So the difference here is basically the error. Oh my goodness. The only thing worse than me trying to draw is me trying to like write with my mouse. So basically what we're doing is there's a difference in error, right? And if we take a step in the wrong direction, the algorithm acknowledges that by comparing the well, basically the change in error. So when we talk about the derivative, it's basically what is the change in whatever value, the weight in this case that we're talking about in the case of a neural network, and how does that change the error in our prediction, okay? And so backpropagation is the process of calculating this gradient. The optimization, and the updating, so basically taking that error, saying, oh, that's too high, and applying it to your, to update your weights is what gradient descent does, okay? And so this is just one step. So if we step in this direction again, so the algorithm will basically say, oh yeah, this is going in the right direction, right? I'm reducing my error. It will take another incremental step this way, right? And for each iteration is going to walk through until it converges on the minimum value of error, because as soon as it starts getting here, it's going to be like, oh, well, I'm overstepping, right? Okay. I really wanted to make sure you guys had a graphical explanation before I dove into the more formal explanations of some of this stuff. Okay, so our goal tonight is to put all that together and build a multi-layer perceptron from scratch, effectively. And so going back to our objectives, we're going to walk through a simple example, one turn of that backpropagation gradient descent, and then we're going to implement it from end to end and compare the our implementation, writing it from scratch, versus what's known as stochastic gradient descent if we have time, and we'll be able to compare the two. Okay. So, okay. So what is backpropagation? Backpropagation is short for the backpropagation of errors, right? And so this speaks to how, and the reason it's called backpropagation is because what we're doing is we're basically calculating our weights, and then it's going back. We're calculating our error, and then we're going back and updating our weights. That's why it's called backpropagation, right? And so I am not going to get into the calculus. If you want to, I would highly recommend that you, there's some great proofs out there. Highly recommend you try a couple of these links here, but that calculus is not necessary to move forward, particularly with this sprint. But it is very useful. Okay, so what is a gradient? We already defined that. The gradient itself is basically this slope term here, or the change as we're moving down, and we're optimizing. Okay, so talking about a different example. And so what I actually want you guys to do is I would love for you to take just a minute and jot this down. Take a screen capture or bookmark this, because we're going to be referring back to this particular diagram several times. We have an example that's going to walk through something like this. So if we have, an input hidden layer, and we have the output layer. And we have 1, 2, 3, 4, 5, 6 combinations of inputs and weights that are combined in this first, in the input to hidden layer. And then we have the x1, x2, x1, x2. That's a presumably an interaction term in our output that influences our output. Okay, so let's get into our code. But before we do that, I want to pause. Are there any questions so far? I appreciate you guys nodding your head. Thank you, Tyler. And appreciate your cameras on, because this helps me not sit here for 2 minutes and wait for someone to ask a question. If you just shake your head, saves everyone 2 minutes. Okay, awesome. So if there aren't any questions, we'll go ahead and move on. Let's generate some random data, some fake data. So in this example, we're going to try to predict exam scores as a function of hours studying and hours sleeping. So in this case, we have 2 features that are coming in, and we have 3 outputs. Okay, 3 training cases in this case. And so we have one guy who spent 2 hours studying, made a wise decision, and got 9 hours of sleep. We have someone else who spent 1 hour studying, probably stayed up very late stressing out about it, only got 5 hours of sleep. The guy who slept well got a 92. The individual who didn't get a lot of sleep got an 86. And then we have another student who was somewhere in the middle. And let's say that she spent 3 hours studying, but got a reasonable amount of sleep. And she got herself an 89. So we have different input values, different output values. Okay. Now, for sake of this, we're going to normalize just to make sure. It's rarely a bad choice to normalize just in general, although it's certainly not required for every problem. Okay, now this is where I want you guys, so this is an entirely demo class. There's no live coding here. It's a lot of explaining and walking through example step by step. So in the interest of making this a more active activity, what we're gonna do is you guys are gonna help me write comments to explain the code, okay? What does NP Amax do? Let's go ahead and find out. So we have our values. Let's call out what is, so if our X values are, so we have X, right? So it's a NumPy array. And if we plug in, okay. So given that, so given this and given Amax, what is this function doing?
Is it giving you like the max score?
Yep. Why would it have an A in front of it?
Absolute.
Returns, yep, Dakota, thank you. It returns the max of an array. So that's why it's different than just max, which would return one value. This is compatible with an array. Okay, awesome. Okay, back to the less intuitive stuff. So what we're doing here, what I'll say is we're building a neural network from scratch, right? But the goal here is to create a class that we can later instantiate, you know, in terms of best practice. So actually, let me ask you guys, in terms of best practice, why would we want to use a class and an instance as opposed to just writing this stuff out as we did yesterday?
It saves us a lot of time.
It saves time. Yep, because there's reproducibility. We're able to use it once and use it again. Why else? Any other ideas?
We could inherit from it later to make changes or modifications without having to recreate the class from scratch.
Yep, exactly.
Create objects.
Okay, what's the benefit of creating objects?
Well, what Gwen said, essentially.
That's also something I said about not being able having to do about being faster, because it's better than having to do the same code again and again.
Exactly.
We just make an object and then we can just pass in and all the functions.
Yep. Awesome. Sounds like you guys got it. The other thing I would add is it allows for much cleaner code. As we'll see later, all of this, when we call this, so let me run this before I forget. When we instantiate this and we call attributes from this class or from this now object, what we're getting is we basically call it with an in, and it allows us to store these variables as attributes and refer to them later with very clean code. And so the reason I mention that is because for production ready code, so to speak, you want to be using classes where possible. Okay. Okay, so before we go on break, let's start with this. So what am I doing here? What comment? Oh, Keith says hi, everyone. Okay, Keith says it's time for a walk long, it's time for break. Okay, so what is a comment that would work here? What are we doing in this block of code?
Establishing defaults for inputs, hidden nodes, and output nodes.
Yeah. More broadly, what are we doing? And what you can do is scroll up and look at the walkthrough of what we did yesterday, right? And so how would we relate what we did yesterday to what's going on here, either in the formal process, the other outlines we talked about? Look at your code from yesterday. How would we describe this? A little less literally, a little more abstractly. I mean, we're
assigning the number of nodes in each
Yeah.
step.
No, you got it. What else? So we're establishing the number of nodes. What does that do?
Like it tells how many inputs there are, how many times it passes input, and then how many times it passes through the calculating the weights and getting the error calculation.
Mhm.
That's in,
Yep,
nodes.
you got it.
They calculate how many times they'll do that, and then
Yep.
the output node is how many outputs you have to show.
Okay, yep. So you guys are telling me what.
So I guess the comment is total number of steps.
Establish number of steps. I would say this, one way you could do it, let's go back up to our formal definition. We're establishing our network architecture is one way to describe it. This is where we assign the number of values, right? You could also, as you guys said, establish the number of nodes in each layer, right? Either one of those, perfect. Okay. I love it, okay. Perfect. Okay. Now what about this one? What are we doing here? What are we doing in this block?
Getting random weights.
Yep.
Every time it's instantiated. Yeah.
Yep. So we are initializing. Oops. I got your beautiful faces in front of the, and I missed some comments. So initializing the default layers, great. I'm going to include that one. I like that a lot. And randomly initialize weights. Perfect. I'm stealing that, Annika. Okay, great. Okay. So this is randomly initializing weights. Okay, but we're doing that twice. Why would we do it here versus here? So what is the difference? So I would actually like to edit this. So we're randomly initializing weights, but what's different between this and this?
Oh, it's the weights for each individual node for layer for the inputs and the hidden.
Yep, exactly. So this is where we initialize the weights between input layer to the hidden layer. Perfect.
Basically, the second weight is the updated weights.
We're not updating anything just yet. We're just establishing random values right now. But that's next. I think you're getting ahead of me. So then what are we doing here? What's a comment that works here?
Weights between hidden layer and output layer.
Yep, perfect. So we're going to randomly initialize weights from the hidden layer to the output layer. Okay, great. So we're going to instantiate our class, create an object, a neural network object that we're storing in the NN variable. And so let's pull our values out of that. So our layer 1 weights, we have 3 values here, 3 values here. Layer 2 weights. So why would we have different, why would we have different shapes of the two layers and the weights?
The layers are different shapes.
Yep, they are, right? If we go back up to our example here, we've got 2 and 3, 2 input and 3 hidden. So why, so what do we think these represent then? Like, so what we have, we basically have a nested array here, a multi-dimensional array. What does this first embedded array refer to? We have 3 values here. What is that? Going back.
It's
Oh,
the
go ahead.
W1, W2, W3 corresponding to X1 in the diagram.
Yep, you are correct. What's another way to say that? So you're saying it's this, this, and this. How would we describe those?
Individual weights for input 1.
Yep, exactly. Perfect. Okay, so let's go back. Okay, and I'm not going to add that as a comment, but perfect. So then why would, oh, someone wanted to say something? Nope, someone just coughed. That's okay. Okay, so then if that's the case, why do we have 3 in this? So we basically have 3 values here. What would these 3 represent? Layer 2 weights.
The class has 2 inputs but has 3 hidden nodes. So it's doing it 3 times.
So layer 2, if we look at the definition here, weights.2 actually refers to the hidden layer and the output layer, right?
Yes.
And so why would we have 3? And maybe I misunderstood what you were saying.
No, because I'm talking about self inputs. Okay, okay, I think I got it now. So from inputs to nodes is 2, it's 2 to 3.
Yep,
So
exactly.
layer 1 is 2 to 3, and then from nodes to output nodes it's on 3 to 1.
Yes,
So,
exactly. Exactly. No, you got it. Perfect. Okay, so let's go and just to sort of like emphasize that before we dive in, and we'll go on a break in 1 minute. Someone's definitely. I just want to like emphasize. Let's watch him throw up on my bed just in protest. Let's print the shape. Right. Okay, so it's a 2 by 3 array because we have 2 arrays, right? Each with 3 members, and each of those members is the individual weight from input 1 into each of those 3 hidden layer nodes, right? I promise this is going to be worth it, guys. It's very important that we follow what's going on here. So then this row represents the weights of input 2 going into the 3 nodes in the hidden layer. Okay, so that said, I want you guys to take a 5-minute break. I'm going to take my dog for a walk before he tears down the door. Timer, 5 minutes. Okay, get up, move away from your computer. You know the drill. I do not want to see you in front of your webcams. We'll see you guys in a few minutes. And if you have questions, please feel free to leave them in the chat and we'll review them when we get back. Okay, welcome back. Got a question from Ashwin. Wouldn't it help if we added an additional parameter for the inputs in the class definition? Absolutely. That would make this a more generalizable class for sure. For sake of this example, I'm going to leave it as is, but I invite you guys in your own implementation to do just that. Make it flexible to additional number of different architectures that you would implement. Okay, give it a, should there be a bias? Great question, Martin. So let's put a pin in that just for a minute because it will come up a little bit later. But Martin and I had quite, and Gwen had quite a long conversation. Actually, Gwen was the one that asked the question last night about the solution to the assignment. And adding another layer, or sorry, adding another term to the array, to the data frame, however you organize the data, actually led to the solution. And so bias is a way to offset if it's converging on weird answers. And so the question was, as Gwen posted in the channel last night, all of my answers are converging to 0.5, right? And so that is an example of when a bias is very useful. So a bias can be used, but it's not 100% required, Martin. So to be statistically accurate, yes, but in most cases, they actually omit the bias. Got it. Okay, good to know. Had bias in its example. Last columns was just one, like the assignment solution. Makes sense. I'm inheriting the assignments from JC, John Cody, so he'll probably have more in-depth explanations in some of the materials than I have time to review in class. So great resource for troubleshooting. Okay. Let's dive in. So welcome back, guys. We see almost everyone. We're still waiting for Raul and a few other people. I see some people. Oh no, Raul, you're there. Were you napping? Nope. You don't. No judgment if you were napping or just leaning back and staring at the ceiling. I just couldn't see you. I see you now. Sorry for calling you out. Okay, let's go ahead and dive in. So So let's talk about, so we're basically just initializing a neural network there, right? So let's talk about feed-forward functionality. So, kiss the keyboard. So what I'm going to do here, this is actually the exact same code as before. So what I'm going to do is I'm just going to copy and paste our comments from earlier, right? So we're initializing the default layers. Oops, I don't want to comment out that first layer, first line, right? There we go. Let's yell at me for indent issues. We're going to randomly initialize the weights for the input to hidden layer, and then we're going to randomly initialize the second set of weights, right? Okay. So what does this slide of code do? How would we explain it generally? And don't tell me it's a sigmoid function. That's not the correct answer. What is a sigmoid function doing? What is the significance of it?
Is it
Sorry.
using the inputs?
I heard two people. I'm sorry, you spoke over
I'll go ahead. I think we kind of came to the conclusion in the walkie-talkie that the sigmoid ensures the signal being passed to the next layer is between 0 and 1.
Ooh, I like that. So the assures the value. So say that again. Assures that the.
It ensures the signal being passed to the next layer is between 0 and 1.
Yep. Great. What would we formally call the sigmoid function? How does it relate to our process that we talked about? Activation function. Exactly. It's an activation function. Yep. And so the sigmoid. Great. Okay. So what we're adding here is the feed forward, basically just like the process that we walked through last night. So those steps that I was like, yay, we did a neural network. Taken together, those steps put together a feed forward algorithm. So refer to your notes from last night if you want to. What are we doing in this step here? So we're taking the hidden sum is going to be the dot product of x and the weights. So what is that doing broadly?
Generating weighted sums?
Yeah, exactly. So we're combining x, the inputs and weights in a weighted sum. Yeah, exactly. And so that is being passed into, and the reason we call it a hidden sum is because this is what is being passed into the hidden layer, right? So what about this function? Self-activated hidden, self-sigmoid, like what is all this?
We are applying the sigmoid function to the weighted sums.
Yep. So we are applying the activation function to the hidden layer weighted sum. Okay. Can we add a little more detail to it? What's another way to, I mean, why is it called activated hidden? So let me answer that one. I would like to call these activated values from now on, right? And so this is to, because basically we have our weighted sum and then we're applying a transformation. And so I'm gonna call these our activated values, okay? Or activated weights. It makes a little bit, it's not quite the weight, it's a weighted sum, but I wanna call these activated values moving forward, okay? Okay, so then that said, what could we, what will we put here?
Combining activated values with the weights. I mean the second weights that we did of the second layer between the hidden and output.
Could you say that another way? I guess what I'm listening for is weighted sum. So this is another weighted sum, right?
Yeah.
Between the, and I'm sorry if you said it and I didn't hear it. So we want the weighted sum, but it's between the hidden layer and the output, right? And it's implied that it's the output because it's the weighted sum of the output. Okay, last one. What would we put here?
Apply activation function to the output weighted sums.
Yep, to the weighted sums from the weighted sums of the output. Yep, perfect. Or to the output. Let's just put output weighted sums. Perfect. Okay, you guys got it. So let's go ahead and run it. Okay, cool. So let's try to make a prediction with this. Okay. So just to step back, we did that one step at a time. So what are we doing? We have a sigmoid function. In our feed forward function, we're going to, I guess it's technically a method. We're applying inputs, right? And getting a weighted sum of the values between the dot product. So it's between the input and the and just the randomly initialized weights, right? We're going to apply the activation function to those values. So we have a process here. So we multiply the inputs and the weights to get the weighted sum, and then we transform the weighted sums. And we do that twice. So we do it on the input, right? And we transform them into the values going into the hidden layer. And we do the same thing here where we take that, what was passed in. So that's what I just described here, right? These are our weighted sums being passed into the hidden layer. We're gonna apply the same logic. We get a weighted sum that's then being passed into the, passed out as the output, right? Where are we? Sorry, scrolled a little too far, right? And then we're basically returning that activated output. Okay, so let's run it. Okay, and there's the reason that I'm calling it activated here. Okay, so let's make a prediction. So we've instantiated our neural network. We have our output, and then we're printing our input, and then printing our output. And so we're actually only printing out the input for one person, right? So we basically had, let's review what the whole thing is. So if we have X, okay, so we have, in this case, and just to be clear, I need to call this out. This is actually slightly different than what we were talking about before. But what we have are inputs, 0.6667 and 1, right? The output is 1 value. And then, right, input here is 1 level of that input array. We're trying to make a prediction. And so if the output is 0.66, if our actual value is 0.61, anyway, all of that to say we have an output coming out. Okay, so let's move on. How do we know what that looks like? What is our error is the difference between the Y value in that, for that first observation, minus the output, our predicted value, right? So what is that actual value, right? So the array itself, so our Y value, our actual Y value is 0.009, and our error is actually pretty big, right? So the reason I say that is, yeah, negative 0.6 is a small number, right? Relatively speaking. However, relative to what our actual value is, our correct output, it's 0.009. That's a pretty wide error, right? So looking at printing out all the outputs and all the errors, we have so basically reapplying the same logic, but using it from our data set above, we've got 0.61, we've got 0.6, 0.61 versus, you know, errors that are kind of big, again, relative to that initial value. So why are my errors so big? A couple of reasons. The prediction itself is really small, right? So that value that we reviewed, the Y value, is small, right? And so whenever you have, it's harder to, this is a really difficult point to explain, but so let's just say that if you have a small number, let's say you have a 1 in 200 chance of having something happening, right? That means, but let's say that when you're doing your sampling, you get 2 out of 10, right? You've only had 2 absolute events that have happened, right? But because it was such a small sample size, you're more likely to have large error. And remind me to talk to you guys about small sample sizes and bias in medicine. I'm not going to go down that rabbit hole right now because we need to finish this, but it actually produces some very, very serious problems in the scientific literature. So small values or rare events can result in really high error rates. It could be because the second layer weights are really low. Could also be that you know, the weights, the way they came out were, you know, just randomly bad. I mean, so there are a couple of things that we can do. So we could go in and manually update our weights. Obviously, we're not going to do that. Not recommended. Other options would be bigger than we have an understanding for. Just want to make sure I'm getting all the points. So basically, we know that our inputs, our X and Y, are correct, right? We know that our activation function is working, right? I mean, in the real world, it might be that there's a typo or something. So what's going on? It's the weights, right? And so what we want to do is we want to go through and update those weights, right, to make a better prediction. So all of that muttering to say we aren't going to change as part of this algorithm the inputs. We're not going to change the true Y value, the true target value, right? So what can we do to improve the, reduce the error? Well, we can change the weights. Okay, so this is where things start to get messy. So let's talk about gradient descent in action. Okay, so we've already assigned these comments, so I'm going to go ahead and skip these, but effectively we're expanding upon our neural network class. And what we're going to do is initialize our neural architecture. We're going to assign some random weights for each, between each of those layers. We have our sigmoid function. We're also going to define the derivative or sigmoid prime, okay? We actually talked about this last night, but this is where the calculus comes in. This is where we take that derivative. And let's talk about the feed forward step. So we've already done this. We've done this already. So let me go ahead and copy and paste these comments in, just so that we have it and I'm not constantly scrolling back up. Right? Okay, so now we're layering on the backward propagation. Okay. This one is a little bit trickier, but I think it's a little more obvious, actually. So what are we doing here? We have O error, and we're basically taking Y minus O. What does it look like we're doing there?
Error of the Y minus the output.
Yep, exactly.
Yeah.
We're calculating the error, which we did last night, right? Calculating the error, or the difference between the true y value and true y value and the predicted value, right? The output. So then what we're doing, so what are we doing here? We've got a value O delta, and delta is a Greek letter that generally means change, rate of change, giving you guys some hints there, which is going to be a product of the error and sigmoid prime. So what do you think's going on here?
Multiplying error by the derivative of the activation.
Yeah, this is true. Why do we want to do that? Why do we care about O delta? And if you, if
Will that
this,
get us like our slope for the gradient descent?
yep, well, yes and no. So yes, it's definitely a slope, but basically it tells us how far off we are, right? How far off are we on the sigmoid function, okay? So remember, we're applying the sigmoid value, right? So these are basically activated values, right? So these are transformed. And so, yes, it is basically, if we're thinking about this process as like part of the, oops, that is a very poorly, okay, anyway. There we go, right? Where this is 1 and this is 0, right? Our slope, so what we're looking at here is the derivative on our sigmoid, right? And we're multiplying it by that, right? And so this is where it gets a little bit weird, and if it doesn't 100% make sense, that's okay. We're basically saying how much farther would we need to go up in terms of the activated value to get closer to the true y. Does that make sense? Okay.
Yeah, so we're calculating like rate of change.
Yes, on the sigmoid specifically, on the activated values. Whoops. I was trying to erase and I ended up not sharing my screen. Okay, awesome. So, okay, so translate that. How could we write that as a comment? And I am watching the chat now, guys, if you guys want to leave your comment in there.
Can I just like have a doubt, because didn't we already apply the sigmoid transformation on y and output in the previous steps? And like to get the output, we would have applied sigmoid function, right? Basically our O.
Yep.
And we're making a difference with the actual output, and then we're applying the sigmoid function again on it?
Yeah, great question. So this is our feed forward, right? So this is one step in the iteration. The next step is actually to say, okay, we applied it. How far off are we? And what this does is this gives us the information we need to update the weights, right? And so basically, does that make sense?
Yeah, but I still don't get like why we should apply sigmoid function again.
We're not applying the sigmoid function again. Sigmoid prime is the derivative of the sigmoid function, right?
Yes.
Okay.
Yeah.
Okay.
Okay.
All right, got it. Thanks.
Okay, so you got it. Help me write a comment. How would you explain this to your to a junior data scientist who's going to be using your code? Sorry to put you on the spot. Someone else can pipe up if you want.
So we're taking the error and kind of seeing in which direction you want to go, like you said the other time.
Yeah.
So we want it on a sigmoid function, so that's why we're multiplying it.
Yep. And so basically that's pretty much it. So oh, thank you for letting us know that you're leaving. Best wishes with your baby, Elizabeth. Take care of family first. Okay, so basically which direction do we want to go, right? So that does inform that question. So apply the sigmoid derivative to the error, right? Which gives us the change. So delta means change. So basically we're defining how we want our output, how we would change the weighted sum or the activated. This is why it gets abstract. So it's transformed, right? So when we go from, we're basically going from here backwards, right? And so we're saying we have an error, right? And the backward propagation piece is working backwards like this. And so we're going to take that sigmoid, because it's a transformed value, and use that to update our weights. Okay, again, I know this is super abstract. That's why we're going through this slowly, right? Okay. And I see Jeffrey typing, so we'll pause for a second. I see some, and it's completely understandable. You guys are going to have questions here. Let's clarify it. Awesome. Thanks for that recommendation, Gwen. Oh, no. Okay, bye, Jeffrey. I hope we see you again in a minute. Okay, so no, okay. Okay, so which direction do we want to go? Okay, so hold that thought. Remember that, guys. Okay, so what are we doing here then, right? So we basically we're taking, and this is where it gets really abstract, right? We're taking that delta, that change, and we are taking the dot product against the weights, right? A transformed value of the weights, and we're calling that Z2 error. Okay, let's unpack that. So rather than put you guys on the spot, effectively what we're doing is we're applying the delta, that correction, if you will, to the weights, to weights 2, right? Now let's go back. What are weights 2? Weights 2 are the relationship between the hidden node and the output node, right? So again, we're going back, we checked our error, we looked at what the error was, how we want to make a correction, and we're going back and applying it to this weight, to these transformed weighted values, weighted sums. Okay, that's a lot. Okay, this is the problem with scrolling back and forth, okay? So I'm actually just going to fill this in. So we are applying our adjustment. I'm just going to call it adjustment. The O delta to the weights, to the transformed weights. Okay. And so we're going to do the same thing. We can talk more about this in depth during office hours tomorrow, so I don't want to skip over this, but we're effectively doing the same thing, right? So we have Z2 delta, right? So this is the back propagation piece, right? We're moving backwards. So we're propagating that adjustment. We just did it from here to here. The next step is to go from here to here, right? And update the weights that way, okay? So let's just go ahead and go through this. So what are we doing here? So Z2 delta, so this is basically our, we're creating that error term, right? We've got the error term, and we're applying that sigmoid function, that transformation, to create that delta term. Okay, so this one's a pretty straightforward one. What are we doing here? This one should be a little more self-evident. I know it looks a little bit like Greek, but read the names of the Like, what's going on here?
It's applying adjustments to the inputs.
Yep.
Weights.
The weights, right, exactly. So we're applying adjustments to the weights. Perfect. And we're doing it, so we have weights 1, right? Awesome. You guys got that? No, seriously, you guys are awesome. I was really concerned about this because this is not an easy task, but I really want to give you guys a shout out. You got this. Okay, cool. And then we're defining another helper function to train. So okay, now that we've broken it out, let's actually see what's going on. Okay, so we have our updated definition, right? So we have a neural network. We have our sigmoid prime. We have our feed forward piece, which is actually going to be to apply all the weights and make a prediction, right? And then the backwards propagation piece is making updates to those weights in reverse, right? So let's go ahead and print out what those errors are one at a time. Okay, so our errors are negative 0.7716, negative 0.73, negative point. So those are pretty big relative to our actual values. So what were those actual values? So the actual values were 0.92, 0.86, and 0.89. So the error is large relative to our actual values. Okay. So looking at that number, so O delta, remember, and I'm actually going to do this. Where's O delta? This is why I wanted to get comments in particular. So let's go ahead. So we're defining O delta. Let's make sure yep. Okay. This is the code, right? So when we generate, there we go. Okay, so what is happening here? We're taking the error, and remember what are we doing? We're trying to take the this is the gradient piece of it, right? We're taking the slope, and then we're calculating that, we've got that activated value. And that's our delta. That's how much correction we're going to make, right? Okay. And so that tells us sort of like this is directional, so it tells us which direction to go. All of them are kind of going in the same direction. Now let's look at the error in the second, so now we're starting to do the backpropagation piece, right? So we're going from the output layer to the hidden layer. So we're talking about the Z2 error. Let's go back and pull in our comment from there. So this makes a little bit more sense. Okay, so what are we doing here? We're applying our adjustments, right? And so what does that actually look like? Well, we have a 3 by 3 array. Why? And so this is where I want you guys to answer something. Why would we have a 3 by 3 array here?
Is it because we transposed it in the function there, and so it came out a different shape than we would originally have expected?
It's a little more abstract than that.
Okay.
You're not wrong. It is transformed, in fact, right? Because we have the D. So basically, what I want to highlight here is that these are the errors from the output to the hidden layer, right? And so how many values are actually being passed into that? Let's go back up. So this is kind of strange, but let's walk through it. We have 3 layers here, right? But how many values actually went into that weighted sum to produce this? We actually are carrying the values from here, 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 here. So the back propagation step of at this level, going from here to here, applies error and adjustments to all levels. Okay, so these are activation values, but basically the reason it's a different shape is that we're not just going from here to here. There's value in updating all of them accordingly. Okay, and that's just part of the that's part of the algorithm. Okay, so let's see, where are we? We're on our second error, right? Okay, so let's look at the next gradient. Okay, so this is this is another example of activated values, right? And this tells us how much on that sigmoid we'd want to move in the other direction, right? But more importantly, this is the delta. So this is the correction we're going to be applying, right? So this is the error itself, and this is the error for all those weights, and this is going to be then applied. Okay, so then we're going to be applying all of that to, let's see, where are we? Okay. Okay, so my question here is, we're applying our adjustments. We basically now, so all we've done here is we haven't actually applied anything. So all we're doing here is we're stating what our delta is, and we're stating our error, right? So the error is transformed. It gives us the delta itself. And so now we have all the information we need to actually update our weights, okay? And we have weights, we have 9 of them because we actually have 9 weights that need to be updated, right? For each of the different interactions, 6 between the input and the hidden layer, and then we have 3 between the output and the hidden layer, right? So yeah, we're basically going to be applying that. Okay, what else is going on here? So xt dot neural network 2, so we're applying it via the dot product, right? And then we're doing that to, let's see what's going on here. I have to remind myself. I want to be sure that I'm on top of this as much as you guys are. Okay, so we are applying, oh, okay. We're applying the dot product to the inputs, right? Okay. Okay, then we're going to apply, okay, so then we're also going to be applying sorry. Okay, so we're applying it to the inputs, but we're also applying it to the values coming into the hidden layer. Okay. So, okay, let's unpack this. Let's step back. Why would we want to multiply the gradient by the inputs? Like, why would we care about this?
That's how we actually like move down our slope with gradient descent.
Yep,
Yeah.
exactly, right? And so yep, exactly. Now so how would that be different? Oh dear, okay, so my question is, how is this different than what's going on here, right? So we're applying it to the inputs here, but here we're applying the output delta to our activated hidden values.
It doesn't seem all that significantly different to me, just that we're doing the same thing to a different layer, making sure to use that layer's associated values.
Exactly, and so the inputs are effectively what's coming into, or that's what's being passed from the input to the hidden layer. This object includes the values that are being passed from the hidden layer to the output, right? Okay. It's late. There's a lot going on. I'll just, I'm gonna fill this in. So basically, we're going to change the, let's see, how would we best describe this? Let's say, well, actually, no, I'll ask you guys. And Gwen, you seem to have a good grasp on this. What comment would you put here?
Update hidden layer weights.
Yeah. Well, yeah, that is okay. And then we are, okay, sounds good. Okay, we're running short on time and I want to be sure we actually, now that we've talked through the whole darn thing, let's see it in action, right? Okay, let's do this thing. I knew this would take forever. Okay, so let's actually run through it. What does this look like if we were to train something, right? So going back to our example, what we're doing is we've got, we're iterating through 10,000 times. We're going to print out the first 5 epochs, and then after that, basically every 1,000. We're going to print out our input. We're going to print out the output. We're going to print out our predictions, and we're going to print out our loss, right? Our error. And so just to clarify, error is something that I was referring to internally within it. Loss is going to be at the epoch level, right? So what is the difference effectively? What is the mean squared error of the difference between our predicted value and the actual Y value? Okay, so let's walk through it. So our inputs are some values. Our actual output in that first, so our actual scores are 92, 86, and 89. Our predicted outputs are pretty awful in comparison. So if we're expecting 0.0092, we've got 0.0058, 0.0126, 0.0056. That's not great, right? Let's go ahead and walk through a couple of epochs. I'm actually not quite sure why it didn't print out the first few. Oh, here we go. Sorry, I scrolled down, that's why. Okay, so epoch 1, sorry, my bad. So actual output. Okay, so actually this is way off. It's still way off. So we have actual values. We have 0.0092. The predicted output is like 0.71. So that's at least 700 times what we would expect it to be, right? So even though this is a small value, we want to compare it to the actual value, our true, value. Way off. Our loss function returns 0.48. Okay. As we cycle through, we have our actual output, which is 0.092, and we're 0.57. So we're getting closer, right? We're going lower as we should be, and our loss accordingly is dropping. And so what you're going to see is as we scroll through these, the loss keeps getting lower, and in other words, we're trying to find the minimum. That's the gradient descent piece, right? We're trying to find that minimum value and converge on that lowest value. And so it keeps getting smaller and smaller and smaller as we run through these. Our loss gets very, very small, almost effectively 0. This is epoch 3000. We have a value of 0.0092. Our predicted output is 0.0067. So we're improving, right? Yeah, so by the time we get to epoch 10,000, we've got our actual output is 0.0092. We've got 0.0057, which is still not great, but way better than we were before. And, there's very, very small differences between the steps. And so it's kind of consistent with our visual from before. You're going to make really big gains early on. The steps are going to be longer generally, but it's going to have diminishing returns, right? So there's going to be smaller steps and smaller differences in loss. So smaller improvements to the error, so to speak, right? Okay, so all of that said, with 10 minutes left, we have implemented from scratch a multi-layer perceptron, say that 6 times fast, with backpropagation and gradient descent. Okay, now when you guys are reviewing, what I want you guys to do, go back and review those comments that we wrote together, okay? Those are our notes. That helps you explain. And I want you to recognize that a different class may have different comments, okay? This was our collective learning experience. You guys help put that back together. Looks like Hills. Yeah, and so Gwen, excellent point. Something that we didn't touch on is that if we have an optimization problem that looks like this, yeah, you know, steps are going to get us closer and closer, right? However, they're rarely that simple. You'll often have something that looks like this, right? And so depending on how you optimize, it might get stuck in a local minimum, right? And so there are things you can tweak. Yep, local versus global minima. And so this is what we call a local minima, because it's a minimum, but only local to that area. The global minimum is really what we're trying to optimize for. And so this is a very, very simple example. We will talk more, you will get sick of hearing about gradient descent. The goal was to make an introduction, give you the intuition, and really walk through the steps involved. And to be clear, for your sprint challenge, I have, so we'll spend the next 10 minutes reviewing something called stochastic gradient descent. This is just a proof of concept, okay? Go back when you review the recording. Hopefully you don't have to, because I know all of you guys came away with 100% understanding of gradient descent today, right? Right? Yeah, you do now, right? As you're reviewing for your sprint challenge, go back and review this piece of it. This next part is purely for demonstration purposes. This is what's called stochastic gradient descent, okay? And so to your point, Gwen, about getting stuck in local minimum, one way that people try to get around that is by using something called stochastic gradient descent. It's also improved, it's also more, it's more effective, like it's faster. Basically what they do is they take a random subset of the entire thing, calculate the gradient on that, and use that as representative of the greater sample. That's kind of how stochastic works. Stochastic just means there's more of a random element to it. There's a random sample that it's applied to, and that's used to represent the whole all the other values that are not in the sample. And so this implementation of stochastic gradient descent was stolen from Welsh Labs. I'm not going to go through all of these. This is more, again, just for you guys to recognize that there are other ways to apply it, but you're going to see very similar steps where we have our hyperparameters, right? So we have different layers. We could modify this. We could, as a hyperparameter, remember hyperparameters are levers we can pull or tweak to adjust how our learning algorithm learns, right? And so one hyperparameter, which I would encourage you guys to dive into, is adjusting how many layers you have, particularly how big is your hidden layer, how many nodes are contained. We're going to randomly initialize some weights. We're going to propagate through the network in the forward fashion like we did before. So we're basically going to go through and apply all those weights. We are going to apply the sigmoid. We've got a sigmoid. We've got the sigmoid prime. We've got our cost function that is basically the sum of squared error. Let's not get into the, anyway, all of that to say, let's go ahead and run this. There's a couple of helper functions here that you do not need to know. just to help this run. If we implement this and we run it, you know, very, very quickly. So basically I ran that and very, very quickly got a pretty low loss rate, right, on the same problem. And so actually better, you know, in 13 iterations instead of 10,000 iterations like we saw before, we have a much, much improved loss, right? And the other thing to mention is that for sake of learning, we built it from scratch. You're never going to do that in, okay, I don't know, they may ask you to do it on the sprint challenge, but after the sprint challenge, you're never going to do it. I promise. You're never going to have to build one of these from scratch unless you're teaching people how it works, right? I was actually, oh, I can't remember. I think I said it the other day, but like the worst interview question I ever had was implement a, you know, that was the interview question. It was implement gradient descent from scratch. It was a technical interview take home. It was not, yeah, it was not it. That's a lot. And by the way, a good technical take home is usually way more interesting than that, like, because it's their job to give you a taste of the work that you might be doing as a data scientist. And so they give you something that is a taste of the work you'd be doing. Anyway, all of that to say, it's not about showing your math chops. So what is going on with, let's finish this up, with stochastic gradient descent. So in 13 iterations, we went from a really high error rate down to a much lower error rate, right? And this is actually fairly representative of what you would see in the wild, right? That given the fact that it took us 10,000 iterations of, you know, brute force gradient descent in a for loop, and it still took us 10,000 epochs before we got to an error rate that wasn't even as good as this. This is more accurate. This is what you're going to see. So you're not going to implement gradient descent, all of that to stay. In the wild, you're going to be working with stochastic gradient descent, and an implementation of stochastic gradient descent or other stuff is going to be made much, much easier starting next week, because we're going to start working with Keris, which is a, we'll introduce it more formally when I don't have 3 minutes left, but Keris is based in TensorFlow, and it basically makes the magic of neural networks way more abstract, but also much easier in terms of the code. So this is the point at which we walk away from these slow but necessary walkthroughs of algorithms and start moving into more abstraction, but more application. And I'm really looking forward to it. I'm glad we're done with these lectures. Okay, so that said, we have 2 minutes left. For those of you guys that have stuck with me, thank you. I really admire your persistence. A couple people did drop off. Of course, I guess Jeffrey lost power, and Elizabeth had to take care of her baby. So we'll give them an excuse, or we'll give you an excused absence, guys. Those feel like, anyway, so with the 2 minutes left, what questions do you have? Let's walk through them. If you guys are welcome to drop, go to bed, have 2 minutes back. But I will stick around for a couple more minutes to review questions. And I won't have office hours tomorrow, but I believe you have one-on-ones with TL. I'm not going to say, I don't know what TL's schedule is, but I will see you guys on Monday because I'm not online on Fridays. So have a nice night, guys, for those of you guys that don't have questions. For those of you guys that do want to stick around, what questions do you have? Good night, Annika. Good night, everyone else. No questions? I just made your brains explode, didn't I?
I actually have a question from the walkie-talkie we did earlier.
Yep.
We were talking about the perceptron, and I just wanted to clarify, it's not typically limited to a single neuron, but a single layer,
yes,
right?
Yes. Yeah. That's an important, yes, that is actually a very important distinction. A perceptron is right. Yes, and I'm sorry for the confusion. So the simplest perceptron would have one layer, one weight, one output, right? And so that would be kind of like our example where we just had one feature in the linear model where it was, you know, adjusting for square footage as an example. So yes, very good catch. Thank you for clarifying that.
Just to follow up on Gwen before Karthik
Yep.
asks. Thanks for clarifying that, Gwen. Are perceptrons ever used in the wild?
Multi-layer, yes. Single layer, no.
Okay.
So actually the simplest,
But why do we talk about perceptrons then?
so because it's the simplest model and it allows us to walk through and do it. And actually, to the best of my recollection, the multi-layer perceptron, I think is, I'm not going to say that, but there is a multi-layer perceptron implementation in scikit-learn. Scikit-learn, however, does not have a lot more of those advanced neural networks, which is why we rely on additional frameworks like Keras and TensorFlow to start working them out. And this is our point of departure from scikit-learn. So I would recommend, if you guys want to do a quick implementation of a multi-layer perceptron, go ahead and jump into the scikit-learn implementation. Dakota, I think you were going to add something.
Yeah, I was typing it out. But the definition that we arrived on back in DS1 for the Z2 error and the Z2 delta.
Okay, so what, where are we? Is that?
In the backward function.
Okay. Backward function, Z2 error, okay.
Okay, so for error, it says you're applying the adjustment. I thought the Z2 error was actually just the measurement. And then the Z2 delta was the application.
You're right, because, and actually this was my, okay, so this is a really important distinction. So you're applying the adjustments down here, you're just defining what those, so how would you rewrite this? Let's put it that.
Back when, I think what we ended up on was measuring how much the hidden layer weights contributed to output error.
How much?
I dropped it in Slack there too.
There it is. Sounds good to me.
Yeah, I'm like, well, it's been a while, so I don't know if my definition's right or not. But,
no, and you're right. So what are we doing? So the delta is, yeah. So, well, you're not wrong. So we're defining the value, right? And the delta is actually the adjustment, right? This is just the error itself. Yeah, you're correct.
More of a measurement.
Yeah, exactly. Which is needed to calculate the adjustment. Yes. Okay. Cool. Any other questions, guys, or call outs?
Another one, like we discussed in the walkie-talkies, can we have multiple activation functions in like the neural network?
Well, we were talking last night about biological neural networks, and that was one of the distinctions we came up with is you had different activation functions for different types of networks. What do you guys think? So Gwen, I see you wanted to comment, or someone had a, or
I do. I was under the impression that individual layers could have different activation functions. Is that incorrect?
Technically, you can. Generally, this is where I sort of reveal the fact that I'm a little bit naive. I don't use neural networks that much in the wild, and I'll admit that. Just because the work that I do isn't conducive to it. I work on really small sample sizes generally, and it doesn't necessarily, we don't need, most of the questions can be answered with classical problems. So technically, yes, you can. But generally, I think it's just one that's used. And certainly most examples are going to have one. I genuinely can't think of a use case where you would have multiple. Not off the top of my head, but I can look into it. I'm actually really curious now. Okay, any other questions, guys?
Just one, or sorry, or maybe Karthik, you want to ask something? Oh, you already did, sorry. No, if you go up to that snapshot picture again, that, the one that you wanted us to refer to.
Yes.
So, still quite not getting, if you're going to make a perceptron out of this, which piece would you cut out? Is it that middle layer?
That is a perceptron.
Oh, this is a perceptron.
It's a multi-layer perceptron. Yes.
Oh, sorry.
Yeah, that's okay.
Yeah.
So what would a single layer perceptron? That even exists?
Yes, that's what we did yesterday. So hold on, let me bring up. So it's basically, I want to bring up that.
Yesterday was just one.
Sorry, 2 days ago. Right, it was a very simple application of this. So let me.
So I think it'd just be minus the red.
Module, hold on. Module 1, Intro to Neural Networks. Okay, I want to bring up this diagram. Well, 2 diagrams really, to revisit the one we did yesterday. Okay. Okay, so this is effectively a single layer perceptron, right? We don't have a hidden layer, right? The feed forward diagram here is a multi-layer perceptron, right? So basically we have one input layer leading to the output, right? So there's one layer, there's one level of action being taken here, right? If you have a feed forward, in this case, multi-layer perceptron, it's the same concept. It's a feed forward approach, but you have different levels. So you have the input and the hidden layer. Does that make sense?
Is it possible to have 2 hidden layers?
Oh yeah.
For perceptron?
Oh yeah, absolutely. Yeah, that's actually a hyperparameter, is how many layers do you have, how many nodes. But this is I mean, I know it sounded very complicated as we were walking through it, but it's actually a very, very elementary implementation of a perceptron, and it's just for learning purposes.
Okay, yeah, that helps clarify it.
Okay, cool. And we will be diving into recurrent neural networks. We're going to dive into long short-term memory neural networks. Feed forward. Remember where I said feed forward was where basically everything goes in this direction. We diverge from that when we start having these feedback loops here, right? So if you really want to get ahead or you're really curious, LSTM, recurrent neural networks, those are a big deal. We'll definitely be talking about those. There's a lot more here than we're actually going to be talking about. This is just for demonstration purposes, basically. So I've worked with Markov chains, but we won't actually work with those deep convolutional networks. Yeah, there are a lot of terms here that are probably familiar to you guys, but we've got to start with the basics.
Can I just one super brief question randomly, just really quick? You know, yesterday the office hours we talked about CPUs and GPUs. Yep. I assume all these calculations are done with the CPU on Colab, and then defaultly on I did it through Jupyter Notebook. Are we going to be doing things where we use the GPU?
So you can't. I think you can switch to a GPU.
You can on Colab.
Colab. I haven't really found a purpose for it because I only use Colab for teaching purposes.
Can Tina and Dakota comment then?
Some of the TensorFlow / Keras practice I've did, I certainly uses the GPU backend, and it's super efficient for image processing stuff.
Yeah.
and stuff like this. So definitely we will be, well, I'm not sure if we will be, but there are definitely use cases where you absolutely want to switch to GPU backend.
Well, we have to toggle that is my question.
Absolutely. Mm-hmm.
Okay.
Yeah. And I don't, and I'm genuinely not familiar. So I know we're going to start moving into AWS and using SageMaker, which is the Amazon equivalent of, and I don't know. You can get it, but I don't know that the credits that we're using are going to allocate as GPU resources. But then again, I'm new to the whole, I've used SageMaker extensively, but I haven't had much need to apply a GPU or use a GPU to solve the problems I work on. So, okay, cool. Great questions, guys. And thank you for the clarification, Dakota. Have a great night, everyone. Bye, Martin. Bye, everyone. Welcome back, Tyler. And good night, Tyler. And Raul and Leo and Karthik and Gwen and Tina. Good night, guys. See you next week. Bye.